everyone, this is Chapter 8, which is on gases. So one reason why this is really relevant in the medical career is that we use gas with humans. We breathe gases, we breathe oxygen in and CO2 out. And this is not only important in our blood and oxygenating our cells, it also maintains our blood's pH at 7.4. So we have to use different technologies to help people with this when they are sick or injured. And all of these gas laws that we'll learn about relate to how we use some of this therapy. So here's an example of somebody with COPD using an oxygen tank. So the way that this person interacts with the oxygen tank and the way that it provides oxygen to through their nose and through the tubes, all of that relates to the gas laws that we learn in this chapter. Okay, so first we have the kinetic molecular theory, and there are 5 parts to it. So I'll just kind of read through those. For something to be a gas, it has to move randomly at high velocities. It has to have very little attractive forces or repulsive forces between the molecules, so the molecules aren't really interacting with each other in the gas. It has to occupy a large volume, a very large volume, than if it was not a gas. And they have to be in constant motion, mostly straight lines. And then the Kelvin temperature has to be proportionate to their kinetic energy. So if all of those things are true, it's probably a gas, and it obeys some really specific rules. So here are some properties that describe a gas. We look at pressure, volume, temperature, and amount, and we're going to use all of these different parameters in the equations that we'll look at. So pressure is how much force it exerts on a container, and that can be measured in atmospheres, millimeters of mercury, torr, or pascals. We'll look at all of these units of pressure. You'll run into them at different times. And then volume is how much space it takes up, and those are measured by liter or milliliter. Temperature is the kinetic energy of the particles, and that is measured in Celsius or Kelvin. And usually Kelvin is used for the calculations that we'll use later in the chapter. And then N is just the amount of gas, and we can use moles or grams to calculate that. So volume is the first thing we'll look at. Volume is how much space it takes up. It's usually in liters or milliliters. And we will see how this can change when we change some of those other parameters. Temperature is the average kinetic energy. It's usually measured in Kelvin. So if you see a measurement that's in Celsius, you might have to change it to Kelvin. And if we decrease the temperature, there's going to be fewer collisions, so the temperature or the temperature will decrease. And then if we increase it, there's going to be more collisions. So that's why it has to do with kinetic energy. Okay, next one is pressure. Pressure is, again, how much force the gas is putting on the container, and it can be measured in these different parameters. Also PSI, that's one that you use in your tires, that's also pressure. And we look at atmospheric pressure, which is the pressure that the atmosphere is pushing on us, and at sea level it's about 15 psi, which means there's about 15 pounds per square inch pushing down on every square inch of your body at sea level. I think it's probably about 12 psi at the altitude that we probably live at. And we use a barometer to measure pressure. And I'll explain how it works here, and then I'll look at the units of pressure with you. So this is like an old-fashioned barometer, and what you had was like this container, like a bowl of water, and then a tube here. And the water could go up the tube on its own, and there was no oxygen, no air particles, nothing here at the top, just a vacuum. And so what would happen is the atmospheric pressure would push down on that water, or in this case mercury, and it would push it up the tube. And then so the further it went up the tube, the higher the pressure on this on the mercury, so the higher the atmospheric pressure. So this is the first way that they started measuring pressure, And they used millimeters of mercury because they were looking at how high the mercury went up. 760 millimeters of mercury is equivalent to 1 atmosphere, which is atmospheric pressure. And that's also equivalent to 1 torr, named after Evangelista Torricelli, who was the inventor of this barometer. So those 3 units are equal to each other, and you'll need to do some conversions between those. Here's some other units for pressure. And you can see that 1 atmosphere is equivalent to all of these. So this is how you would do those conversions. So there's PSI. 1 atmosphere is about sea level PSI, which is about 15 pounds per square inch. And you also have pascals and kilopascals there. So atmospheric pressure is just that pressure that's pushing down from the atmosphere, the air molecules in the air. And as you get higher up, so as your altitude increases, that pressure is going to get less because there's less air molecules stacked on top of you. So it's kind of like being all the way down at the bottom of the ocean compared to like higher up in the ocean. The further down you are, the more water molecules are pushing down on you, and so that'll result in more pressure. Here's some examples of different altitudes and pressure here. You can see this table at the bottom. At sea level, you are at 1 atmosphere, which is 760 millimeters of mercury. And then as you go down to the Dead Sea, which is lower than sea level, your atmospheric pressure is higher. And then as your altitude goes up to Mount Everest, your atmospheric pressure is lower. You also see changes in pressure on hot, sunny days. You're going to have higher atmospheric pressure. On rainy, cold days, you're going to have lower atmospheric pressure. So weather also changes that. All right, let's do a quick learning check. Answer these 2 questions, and then I'll show what the answers are. Let's see how you did. So there's showing the conversions of millimeters of mercury to atmospheres, and then atmospheres to millimeters of mercury. So make sure that you can switch those units back and forth. And then answer these 2 questions. And there are the answers for those. Okay, so now we'll move into the next section. This is the first law that we'll use in this gases chapter. This is called Boyle's law. And this is comparing the relationship between pressure and volume. And most of these laws are pretty intuitive. You've probably maybe never noticed them as a law, but you've probably seen these changes. And so for Boyle's law, when volume goes up, pressure is going to go down. So if you give the gas more space, you have the same amount of gas, same temperature, and you give it more space, the pressure is going to decrease. So you can think of like a balloon or a tire for some of these laws to help you visualize it. Here's a graphic that shows that. So let's say you have a piston, which is like the same as like a syringe or a piston in an engine. If you push down on that piston, you're not changing the temperature in here, you're not changing the amount of gas, all you're changing is the volume. Then you'll see that the pressure is going to get higher. So these 2 are inversely related. If you decrease volume, you increase pressure. This is the formula showing that if volume decreases, pressure increases, or vice versa. If volume increases, pressure decreases. So that's what Boyle's law shows. These are some examples. So if you have 8 atmospheres of pressure and 2 liters, your atmosphere times liter will be 16. And then if you change some of these values, this can stay the same. So here's another way that we can state Boyle's law. These 2 can stay the same. You can make changes to some of these. You have to change both, and then it results in the same number at the end. So here's how this links to health and like medical sciences. When we breathe in and out, we're using Boyle's law. So we're basically changing the volume of our lungs using our diaphragm, and this forces the pressure to change, and that pulls air into us. So I want you to try this as we do it. As you breathe in, you're actually, your diaphragm is moving down, your chest cavity is opening up, and so your lungs are, the volume in your lungs is getting bigger. And so that causes the pressure to decrease, and it pulls air in. So you're kind of creating a vacuum inside your lungs. And then as we exhale, we're moving our diaphragm up, we're relaxing it, it's pushing up, and our chest cavity is getting smaller. So that's causing our lungs to get smaller, and it's causing the pressure in our lungs to increase, and then that's pushing air out. So that's what happens when we're breathing. We're using Boyle's law. Here's an example using the formula P times V equals P times B to calculate some of these parameters. So let's read through this. You have Freon 12, which is CCl2F2. It's used in refrigeration systems. And it says, what is the new volume of an 8-liter sample of Freon gas initially at 550 millimeters of mercury after its pressure changed to 2200 millimeters of mercury at a constant temperature in moles? So you're given 3 variables and you're only missing 1. So let's write down what we're given and what we need. We need the volume too. So here's how you would set up the equation. You'd start out with P1V1 equals P2V2, and then you would rearrange that to solve for V2. So you can see there how they've rearranged it and isolated that V2. Then you just plug in all your variables and you solve for V2. See if you can do this one on your own. You're given the 3 variables here. You're given the 12 liters, 600 millimeters of mercury, and 36 liters. And so you're going to be solving for the pressure. So here's how you set it up. And here you're looking for pressure too. And then you isolate pressure 2 from your equation and plug in your numbers. So your answer is A, 200 millimeters of mercury. Okay, let's try this learning check too. Read the problem and decide which one fits best. And there they are. First one's cylinder B and second one's cylinder A. Okay, try this one out and see if you can solve it. Notice that your units are in milliliters, but that doesn't matter. You don't need to change it to liters. The equation, when you solve it, will come out to milliliters at the end. Here you are setting it up. V2 is what you need. And that's how you solve it. Your final answer is C, 240 milliliters. And then let's try this one with this helium balloon. Would the new volume be A, B, or C? Okay, so your answer is A. It would be smaller, not the same size and not bigger. All right, let's move on to section 3 now. Section 3 is our next law. This is Charles' law, and it's between temperature and volume. So in this one, we're keeping the pressure and the amount the same. So we're keeping the number of moles and the pressure the same, and we're only changing temperature and volume. And so what this one is saying, and you would think of this intuitively too, if we increase the temperature, the volume will increase. So you can think about that in a balloon. If you heat up the air in a balloon, the volume is going to increase and vice versa. So here's an example of that. We have our piston again. And if we have our volume of gas, we're not changing anything else. We're not changing the pressure in there. We're not holding the piston down and not letting it move. If we heat it up, that piston is going to get bigger, so our volume is going to increase. This is our formula here. Volume over temperature equals volume over temperature. So when the temperature increases, the volume is also going to increase. So here's your equation. There are other ways that you can write it. So you can rearrange it to solve for different variables, which you've done before. But here's our, here they're asking, sorry, this is a learning check. They're asking you to solve for T2 based on your equation. So go ahead and rearrange your equation and solve for T2. So there it is. Your final equation should look like this. You're isolating your T2. Okay, let's try this example. So you have a balloon that has a volume of 785 mils, and it is at 21 C. What if you were to lower the temperature to 0 C? What would the new volume be? So the first thing that I would think about is if I'm lowering the volume, the balloon's going to get smaller, so the volume will get smaller. So it's like I took a balloon and I took it outside on a really cold day, and it's going to get smaller. But first, we do have to use Kelvin for our temperature, so we need to convert both of these to Kelvin, which we've learned before. Then we identify our given and our needed. And so we put our initial temp and volume there, our final temp, and then we need our new volume. Then we rearrange the equation, so we're solving for that V2 that we need. We plug in our values, and our final answer is 729 mils, which is smaller volume than 785, so that looks like it's correct. Okay, let's try this one on your own and see if you can solve it. I see that the temperature is given in Celsius. You do need to change that to Kelvin, and then it says to give the answer in Celsius, so you'll change it back to Celsius. So pause the video, try that one out, and then I'll put the answer up. All right, so here we are setting it up. We changed it to Kelvin, and we have our given and our needed. And then we isolate our T2 variable. We solve it and get 443 Kelvin, and then we subtract 273, and our answer is B. Okay, let's try this learning check. Fill in each blank with either increases or decreases, and then I'll give you the answers. All right, so there they are. Okay, we're ready to move on to the next section. Section 4 is the Gay-Lussac's law, and this is our last simple law where we are just looking at two variables at a time. And then we're going to combine all of these laws later. So this law involves temperature and pressure. And in this one, we're keeping all the other variables constant except for temperature and pressure. So we're keeping volume constant and the amount of gas constant. So in this picture here, we have the piston, and we're showing that the pistons, like we can't move the piston, they're staying still. And so when we heat it up, that's going to increase the pressure because we have more kinetic energy in here, so those molecules are going to be hitting the walls more. So here's the formula for this law, and again we have the same picture. You cannot move the piston, that remains constant, the volume. The amount of gas we're not changing, we're just heating it up, and we're seeing that pressure is increasing. So let's do a learning check here. It's asking you to use this equation and solve for P2. And there's what it looks like. This is your final, how you would solve for P2. Okay, so here's our first example. We have a pressure of 2 atmospheres and 18 degrees Celsius in our gas. What if we increase the temperature to 62 degrees C, but we kept volume and amount, moles, the same? So first we do need to change this to Kelvin. So we're going to change both of them to Kelvin, and then here's our given, here is our given T2, and then we're looking for pressure 2. So we would rearrange it for pressure 2. We would plug those in, and our final answer would be 2.3 atmospheres. Now for a learning check. You have 645 torr at 128 degrees Celsius, and you're going to increase your pressure to 824 torr. So you need to find what the final temperature is in Celsius. So make sure that you're in the correct units for these. All right, so first you need to change that temperature to Kelvin. So that's your first step. Then write down your given and then what you need. Okay, so then since we need T2, we're going to solve for that. So we rearranged our equation and we plug in our values, and our final answer is 512 K, and then we subtract 512 minus 273. All right, so a little bit more information about this law. It also deals with vapor pressure and boiling point. So when you have different amounts of pressure on a liquid, that's going to affect whether or not it's going to vaporize when it's boiling. So this relates to like when you're boiling water on the stove and whether or not you put a lid on it. If you do not have a lid on it, if you have an open container, it's going to have an easier time boiling off and evaporating. If you have a closed container, if you put a lid on your pot, this vapor pressure is going to be able to accumulate, and all the water is not going to boil off as easily. So when you have a lid, that's going to affect like the pressure that's building on top of that liquid. Also, altitude matters. If you've ever noticed like the back of containers where like baking directions, if you have like a box of brownies or cake, it might have different instructions if you live at different altitudes. And that's because your atmospheric pressure is also going to affect how water boils and how the cooking process goes. And so you can see here at 760 torr, or millimeters of mercury, which is sea level, water boils at 100. But as you get higher in altitude and lower pressure, water boils lower. And so that's why you're going to have different cooking directions. And as you get lower altitude, like lower than sea level, higher pressure, then water boils at a higher temperature. And that's because there's more pressure pushing down on the water, and it's harder for those water molecules to leave. So if you use something like a closed container or a pressure cooker like an Instant Pot, that's why you're able to get the food cooking at higher temperatures, because it's actually at a higher pressure. And so this relates here again to vapor pressure and boiling point. So you can see here the vapor pressure is pushing down on the liquid, and it's preventing it, or the pressure pushing down is preventing it from boiling. So if there's less pressure, it's going to have an easier time boiling. And then this right here is an autoclave that you might use someday. This is what they use to sterilize equipment. This puts this equipment at a really high pressure. My autoclave, I think I use 1.25 atmospheres. And so the gases in here are at 1.25 atmospheres instead of 1. So it actually can heat up the air and the water at higher than 100 degrees, more like 120. And it's going to kill all the microbes in there. So that's how we use it in like the medical field. Okay, let's do a learning check. See if you can explain why water boils at a lower temperature in the mountains than at sea level. So at higher altitudes versus lower altitudes. And there's their explanation for it. There's less atmospheric pressure up high than at sea level. So it's going to have an easier time boiling. Okay, let's move on to the next section. So this is the combined gas law. So for this gas law, instead of ignoring, instead of looking at two variables and ignoring the other, we're going to put pressure, volume, temp together and look at them all at once. So we're kind of combining the three laws, hence the name combined gas law. Okay, so the combined gas law is here. This is it right here. They kind of have some variables crossed out, but it is P times V over T equals P times V over T. So you should write that down. But you can see here, this is showing how they're combining all of those together, all three laws. We are not considering N at this point. We're not considering how much gas. We're just combining the other three laws. So we're ignoring N. So let's try using it. Remember what it is. Make sure you have it written down. So in this problem, you have a gas that has a volume of 675 mils at 35 C and 646 millimeters of mercury pressure. What is the volume of gas at negative 95 C and a pressure of 802 millimeters of mercury? And remember that N is constant. We're ignoring that right now. So first we need to change these temperature values to Kelvin. So go ahead and change those. And then we can write down what we have given and what we need, which is V2. So here is our combined gas law, and we are solving for V2. This should say V1 right there. So you do the math and solve for V2, and then you just plug in all your numbers and solve, and you get 314 milliliters. Let's try this one on your own. You have a sample of helium gas. The volume is 0.180 liters. Pressure is 0.8 atmospheres and the temperature 29 C. What temperature will the helium have when you have 90 milliliters and a pressure of 3.2 atmospheres? Before you go any further, make sure that your volume units are the same, either in milliliters or in liters, and then make sure you change your temperature to Kelvin. All right, so first you got your temperature change, and then it looks like they changed it to milliliters, but if you changed it to liters, that's okay too. And then you need to find T2. So we solve for T2 with our our combined gas law. So there it is. And then you plug your numbers in, and your answer is your answer is 604 K. And then when you change it to Celsius, it's 331 degrees Celsius. All right, we're on to the next section. So in this section, we're going to start including moles, and that's going to lead us to another law. So remember that a mole is the amount of something. And the cool thing about moles and gases is if you have 1 mole of gas at a standard temperature and pressure, it always takes up 22.4 liters. So this has to do with Avogadro's law. And 1 mole of gas, it doesn't matter what kind of gas it is, it takes up about the same as 3 basketballs. 22.4 liters is about the volume of 3 basketballs. And you have to make sure that you're at the right pressure and temperature, because we know that that matters, that's going to affect how much space it takes up. So this is Avogadro's law. Now we are we're including N for the first time. So this includes volume and N, and we do have to hold temperature and pressure constant. That's super important. So what this is showing here, notice that you have like 6 molecules of gas. And then here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I think. So if you have twice as much gas, then it's going to take up more volume because they're going to take up more room. And so that's a predictable amount. Every single gas at the same temperature and pressure, 1 mole is going to take up 22.4 liters. So let's look at this one and see how we do. If we have 0.75 moles of helium and that takes up 1.5 liters, what volume will 1.2 liters of helium take up? at the same temperature and pressure. So you can just do a proportion for that and figure out what that would be. So here's how you would set that up. You have your proportion of V1 over N1 equals V2 over N2. This is what you're given, and then this is what you need. And so you would rearrange that to solve for V2. And you would plug in your numbers, and your answer is C, 2.4 liters at that constant temperature and pressure. So this constant pressure and temperature that I'm talking about is STP, and you have to have it at the same temperature. That standard temperature is usually 0 degrees Celsius or 273 Kelvin, and then your standard pressure is usually 1 atmosphere or 760 millimeters of mercury. So at those standards, it's going to be 22.4 liters is 1 mole. If it's at another temperature or pressure, then it'll be different. It won't be 22.4 liters, but we just assume that we're keeping temperature and pressure the same. So that's our standard. 1 mole of any gas, doesn't matter what kind of gas, is 22.4 liters. And we're going to use these conversion factors for that at STP. So STP is that standard temp and pressure of 0 Celsius, 273 Kelvin, and 1 atmosphere. So here's an example showing that. It doesn't matter if you have a mole of helium, a mole of oxygen, a mole of N2, or even a bigger molecule gas. They're all going to take up 22.4 liters at that standard temperature and pressure of 273 and 1 atmosphere. They're going to have different masses. 1 mole of helium is going to weigh 4 grams, and oxygen will weigh 32 grams, and nitrogen will weigh 28.02, but they're still all going to take up the same amount of space. So if we had 2.75 moles of N2 gas, how much space would that take up? And so let's see what that would look like. We're going to start with moles of N2, and then we're going to use our mole of volume that we just found, the conversion factor, and find out what the volume would be. Okay, so here is our conversion factor. We're going to start with 2.75 moles of N2, and then we're going to use this conversion factor so that our moles cancel. That means that we're going to have 61.6 liters of N2 at STP. See if you can do these two. This one you're starting with grams, and you're going to have to change it to moles. And then this one you're starting from liters. You're going to have to solve for moles and then solve for grams. So try those two out. Here is how you set up the first two. So you've got your grams of methane, and you've got your liters of helium. For the first one, you're going to go from mass to moles to volume. And for the second one, you'll go from volume to moles to mass. All right, so here's the first one. You're using this standard. 1 mole is 22.4 at STP. And then you're using this standard because this is the molar mass for methane. And for the second one, you're going to use the standard of 1 mole is 4 grams of helium, and then your standard 22.4 and 1 mole of helium at STP. Okay, so here's number 1 up here. You have 4 grams of methane. You convert them to moles, and then you convert it to liters. So 4 grams is going to take up 5.58 liters of space. For your second one, you've got 8 liters of helium. You're going to convert that to moles using your liters, and then you're going to convert moles to grams. So that's going to be 1.43 grams of helium. Okay, let's go to the next section. So finally, we're on the ideal gas law. And this is relevant to camping with this butane gas stove. We're combining all of these things we're combining pressure, volume, temperature, and N to come up with this ideal gas law. And that kind of the key for this ideal gas law is like no gases ever really behave in this way, but this is how we can combine all of these together, and theoretically they should behave in this way. So this is the ideal gas law. This is the equation, putting all of these together. So you can write that down. Okay, so in this equation, you might have noticed a new letter, which is R. R is called the ideal gas constant, and R is kind of a value that sort of like fixes all the other values together and makes them work, makes all the units work together, yes, you could say. And so this is just showing how they calculate R. If you rearrange it and solve for R, and you put all these STP values in, so your 1 atmosphere, your 22.4 liters, and your 273 Kelvin, it equals this number here. So we're going to use this number for R, and you just plug it into the equation when you're solving for it. And we always just use that value, and it just fixes all our units together. And it's not really, like, no gases really behave exactly like this, but this equation gives us a pretty close estimation of how they behave. If we were to use different units here, so this one's using, instead of 1 atmosphere, 760 millimeters of mercury, we would have to use a different number for R. So just make sure that you're using the correct R. If you're using liters and atmospheres per mole K, you use this guy. If you're using millimeters of mercury, liters, and K in moles, then you would use this guy. So make sure that you're using the correct R, or you will get the answer wrong. So let's see if you can solve for this one. You're just plugging in those numbers into your ideal gas law equation, and make sure that you change your Celsius to Kelvin. And it is asking you to solve for atmospheres. So you're going to use that 0.0821 for R because you're in atmospheres. Okay, so go ahead and try that one. So here you are, here's your equation again. You need to solve for P, and this is your given, and then here's your R over here. So since we're in atmospheres, we're going to use that one. We are rearranging to solve for P, and then plugging in our numbers, and our answer is 1.7 atmospheres. Okay, so again, this is just showing the 2 units, so make sure that you're using the correct R depending on the units that you're using. We can also use the gas laws and chemical reactions. So when we're looking at how many moles, we can even predict how many moles have reacted based on some of these other parameters. So these equations are super useful. They kind of bridge physics and chemistry and are pretty practical equations. Okay, so here we have nitrogen gas reacts with hydrogen gas to produce ammonia. So here, nitrogen, hydrogen, ammonia. How many liters of ammonia can be produced at 0.93 atmospheres, 24 degrees Celsius, and 16 grams of sample, and an excess of hydrogen gas? So you're going to solve for how many moles you have here, and then just use a mole ratio to find out how many moles of ammonia you would produce, and then calculate how many liters of ammonia. So this is like at least a 3-step problem. So let's dive into it. Okay, so first you have to make sure that your equation is balanced, which they gave you a balanced equation, so that's nice. Then you are given your mass of nitrogen and your pressure, and you need to convert that to Kelvin. And eventually you need volume of NH3, but we have a few steps to go in between. You do get to use your 0.0821 for R because you're in atmospheres. Even though it's not 1 atmosphere, you're just in units of atmosphere. And then you've got your equation. So here are your steps. You're going to take your N2 grams and convert that to moles of N2. and then use your mole-to-mole factor to convert it to moles of NH3, and then use your ideal gas law to convert that to liters of NH3. Okay, so first we need some conversion factors. We need to know that 1 mole of N2 is 28 grams, so there it is back and forth. We need to know that 2 moles of NH3 is equivalent to 1 mole of N2 because there's 2 moles of NH3 and 1 mole of N2. So there's our conversion factors for those. And then we need to rearrange our equation to solve for N because we're looking for moles of, we're going to solve for moles of NH3. So first we just go ahead and convert it into moles of NH3. So we have our grams of N2, convert that to moles, and then we use our mole-to-mole ratio to get our moles of product. So that's how many moles of NH3 we have, and we're going to put that into here. So we have our moles right here of our NH3, and then we're going to put in our R. So this whole thing is our R. We're going to put in our temp, divide it by 0.93, and we're solving for the volume of our ammonia. And so we get 29.9 liters of ammonia. So this is like the most advanced way that you can use this equation. You're putting everything together. You're also using other stuff that you've learned before and putting it all together. Lots of skills here. Okay, so section 8 is partial pressure. This is pretty easy compared to the other ones and also pretty intuitive. So they're relating it to your lungs here. In your lungs, you have these little alveoli that are exchanging gases with your blood and with the air that come into your lungs. And we can use these gas laws to kind of predict which direction the air is going to flow based on the pressure. And so here we have gases moving in and out of the lungs through the alveoli, which are the tiny little berry air sacs. And it depends on their partial pressures, which is called Dalton's law. So you've got, what, 5 or 6 laws, I think, in this chapter. All right, so partial pressure is defined as the pressure that each gas is in a mixture. And so if you're looking at, let's look at this container here, you have a container that has multiple gases in it. So you have some helium in it, you have some argon in it. The pressure in this container is the same as if you had these two gases in separate containers. So if my helium was at 2 atmospheres and my argon was at 4, and then you put them together in the same container, your total pressure would be 6. So if you were to separate them, they would be like the sum of whatever this was. So here's what that looks like in a formula. The total pressure is each of the partial pressures added together. So it's the total of all the partial pressures. That is your total pressure by all the gases in your container, mixed together. Not bonded, but mixed together. So here's another couple examples. If you had a mole of N2, that would be an atmosphere of it. But then if you had like 0.4 moles of O2 and 0.6 moles of helium adding up to a mole, they would still be 1 atmosphere, and they would still take up the same amount of space at STP, 22.4 liters. Same thing here, if you had these 3, still a mole at 1 atmosphere, they would still take up 22.4 liters. And so we can use this when thinking about the air that we breathe. The air that we breathe is about 78% nitrogen, and that just goes in and out and it doesn't affect us. We don't use it for anything. And our oxygen is about, 21% oxygen in our air, and then we have a teensy-weensy percent of CO2. And some other, we have tiny amounts of argon and different things like that. But this is going to determine what the partial pressure is. So in air, if our air is at 760 millimeters of mercury, which is 1 atmosphere, then our partial pressures of these gases are going to be split up accordingly. So let's think about like if we had a scuba tank. Scuba tank has oxygen, and it's at a pressure of 0.45 atmospheres, and it has helium at 855 millimeters of mercury. Darn it, we have two different units for pressure. And it wants to know what is the total pressure for those two. So we do need to add these two. Unfortunately, they're in different units, so we have to fix that. So first, let's get them in the same unit. We're going to get them both into mercury, millimeters of mercury. So we're changing our oxygen pressure. We get that number. And then we just add those two together. And so our total is, what is that? 1,200 millimeters of mercury, or 1.2 times 10 to the third. So we just add those two together, and that's our answer. Okay, let's see if you can do this one on your own. So you've got another scuba diver. He's got helium. That's probably for floating to keep it light, and then oxygen. And the pressure is 8. So that's the total atmospheres. And if the oxygen has a partial pressure of 1280, what's the partial pressure of the helium? Make sure that you're converting to the same units. You need to end up in millimeters of mercury. So try that one out. And so here's what you're given and what you need and your equation. And here you are converting it to that. And then they're also changing up this equation. So you're going to subtract the oxygen pressure from the total to solve for helium. If you want to just not even rearrange it and just solve it normally, you can do that too. Okay, so here you are, and then your answer is 4,800 millimeters of mercury for your helium. So this does relate to your lungs and how we breathe, like we said before. In your lungs, you are exchanging oxygen and CO2. And then in your tissues, you're also exchanging oxygen and CO2. And so the pressure in your lungs and in your cells is going to be a combination of the pressure of those two. So you can see here they're showing some of those different pressures between the oxygen and the CO2. And then your total pressure would be the sum of those. So in your body, oxygen flows into tissues because the partial pressures of oxygen is higher in the blood and lower in the tissue. So it's going to push it in that direction. And then likewise, the CO2 is going to flow out of your tissues and into your blood because it's also going higher to lower. So that the partial pressure is what makes it go the right direction into and out of your tissues and your blood. So here's an example here. Your oxygen in oxygenated blood is higher and lower in deoxygenated blood, so it's going to push into there, and then it's going to go vice versa from deoxygenated to oxygenated. So they're going to switch places, and that's going to cycle your blood through. And then here's showing partial pressure in inspired air, alveolar air, and expired air. And so you can see there's not really a big difference here, but then oxygen, it's going to move this way, right? And then CO2 is going to move that way, right? It's going to go that way. So that's what causes you to breathe. Okay, so here is your final slide. Make sure that you review all these and know which ones you might want to make flashcards to show which ones are which, and make sure that you can rearrange these formulas to solve the problems. See you next time.